Okay, folks, so this is also going to be a short lecture. This is the lecture that would correspond to Friday's class, Friday, October 29th. It's again a very short lecture, and it's about the beginning of chapter 4, 4.1, which is the introduction to abstract vector spaces. So let us get started. Okay, so chapter 4, which is about so-called abstract vector spaces. And so what's a vector space? So a vector space is a set whose elements are called vectors. So let me underline a vector space is a set whose elements are called vectors. And what can you do with these vectors? So what can we do with them? So that's the question. So we can add vectors. So if we have two vectors, so let's call the set V. So if X and Y in V, then there's some operation X plus Y, which also is also in V. So there is some operation called vector addition, and we'll see examples. Okay, and then there's also, we can scalar multiply. So meaning if C is a scalar and X is in V, then C times X is also in V. Well, we have to say what properties these two operations have. So we can add and we can scalar multiply. So what are the properties? It's what you expect them to be. So the first property is that if we take X plus Y, it doesn't matter the order we do it, it should be the same as Y plus X. We should also say that if we have X plus Y and then we add Z, we have the same thing as X plus Y plus Z. Okay, then there is an axiom, there is a zero, there is a vector 0 in V such that X plus 0 is always given by X. The next axiom is that if the zero scalar times any vector X is the zero vector. Okay, and then another axiom is that for any X in V, there is a vector minus X such that X plus minus X is the zero vector. In fact, we'll see that you can see that this minus X has to be minus 1, the scalar times X. So it kind of falls out that way. And then let's see, so what else? There are a couple of other axioms. So there's the distributive law for scalar multiplication over vector addition. And then there's the multiplicative distributive law, C times D times X is CD times X. And there's one more axiom. I think we want 1 times X to be equal to X. That might follow from the other axioms, I'm not sure. Okay, so this is the list of all axioms that I can think of that it has to satisfy. All right, so let me give you some examples. So example 1, Rn, remember Rn is the set of vectors in n-dimensional space, satisfies all these, is a vector space. That's the one we've been studying all along. Okay, so that's not surprising, but there are other kinds of vector spaces which we don't think of as spatial. Here's an example. Let P sub n be the set of all polynomials with real coefficients of degree at most n. So an element of P of n is a polynomial. So P of x would be of the form a0 plus a1 times x plus a2 x squared all the way up to a sub n x to the n. For example, P sub 1 is all expressions of the form a0 plus a1 times x. That's that would be the set of all things of that form where a0 and a1 are real numbers. Okay, so why is this a vector space? Well, you can add polynomials. In the usual way. So for example, in P1, you can take 2 plus 3x plus 1 plus 17x and add them together, and you would get 3 plus 20x. You could also scale or multiply polynomials. So for example, if I take 3 times 1 plus 2x, that's 3 plus 6x. And you can check that all the axioms are satisfied. So that's our first example. That's our second example. Okay, so that's good. Okay, let's look at the next example. To do that, I'm going to need to clear the screen. Okay, so let's consider the following vector space. It's called R infinity. And this is the set of infinite sequences, x1 of real numbers, x1, x2, x3. But we put a condition on the sequence that the sequence is eventually zero. Eventually zero. So xn is eventually zero for n bigger than some given value. So to the right of some entry, you have to have all zeros. Okay. And if you have two such sequences, x1, x2, etc., and then you have y1, y2, etc., we can add them in the usual way by adding the components, the corresponding entries. So this is vector addition. And clearly it's closed undertaking this operation. And then we could also define scalar multiplication, x1, x2, etc., to be, you do it cx1, cx2, etc. Okay, so this is a vector space. R infinity is a vector space. When we talk about dimensions, we will see that this is an infinite dimensional vector space later. It has an infinite dimension. We haven't defined dimension yet for abstract vector spaces. Here's another example. Suppose we look at the functions, say the continuous functions. Let V be the set of continuous, oops, really bad, functions on the real line, R to R. So if you're given two functions, f and g, from R to R, you can add So you can take f plus g, and that's a new function. And how do you define it? F plus g applied to a point x in the real line is f of x plus g of x. That's how you define function addition. And you could also define scalar multiplication, cf applied to x, you take f of x and then multiply it by c. And so this forms a vector space under this operation of function addition and function scalar multiplication. A similar example is to look at the set of all differentiable functions which have a derivative from R to R, and it works the same way. Okay, so that's really all there is that I want to do from this section for now. This was a very short lecture, and we'll be seeing more examples as time goes on. So have a good weekend.